So now I move into showing you how to develop an embedded SoC. I will show you a general chart that applies to any SoCs, but particularly we're going to take this particular flow chart and actually apply it to developing SoCs on FPGAs. So what we're going to be seeing is there's actually a major division between hardware development and software development. So the very first step that you're going to have to decide when you're actually designing an SoC is which tasks go to software, which tasks go to hardware. So let me give you an example. So one simple example is you're designing a system that does certain calculations, and most of what you do is addition. But every now and then you might need multiplication. So you have an option of actually developing a multiplier on the hardware track, which is actually this part of the flow chart, which is the left side of the flow chart, as opposed to actually going on the right side of the flow chart, which is software. So you can either develop a multiplier on hardware, or you can actually implement an algorithmic multiplier, just basically a for loop with additions. This is basically what a multiplier is. So you have to make that decision, and this decision is based on what type of hardware you want, what type of restrictions you have on the SoCs, how often are you going to use that hardware, and whatnot. So the first step is actually deciding which one is hardware, which one is software. This decision might be a lot more important. So for example, if you're designing a system and that system happened to do some sort of a compression or maybe encryption, so you're going to have to decide, should I implement this encryption on the software side, or should I actually design some sort of a processor that does this encryption or compression for me in hardware, and that actually ease my software to do something else, or ease my processor to do something beside actually the encryption. So first thing you need to do is figure out what your hardware and then what your software is. Once you know, we're going to start with the hardware side, which is the left side in here. You're going to go to the hardware development, and hardware development in its easiest form is actually just drawing some schematic diagram and then connecting these schematic diagrams somehow, and you have to figure out what each one of these boxes mean. And once you do, you can just basically go into the IP catalog or any third-party IPs, and IP stands for intellectual property, and you just basically pick these subsystems off the shelf and just put them together. And in Vivado, there's a utility called an IP integrator that allows you to put all these subsystems together, and you can generate the whole SoC this way, However, most likely you are going to have to go and do some sort of a development for certain IP that you might not just find off the shelf. For some reason or another, you don't have licensing, it's too expensive, there's some prohibitive factors that not allow you to do vendor, or it just might not just exist, and you're going to have to develop your own. So you're going to go with the route of user IP development. So you're going to develop your own IP, and developing your own IP is what we've been doing in this course altogether. So we have designed our own IP and HDL, and you wrote HDL code, whether that's Verilog or VHDL, it's up to you, or even System Verilog. And you're going to design that, and on the other hand, you should also design your own driver. But for now, we're going to just focus on the HDL side, on the hardware side. So you're going to take your own. You might just design it completely on your own, and you don't need the LP integrator at that point. But let's assume that, and we will actually use some sort of a vendor off the shelf. So for example, we're not going to be designing our own processor or implementing our own processor. That's a prohibitive task for this particular course. So what we're going to be doing is we're going to pick one off the shelf, and then we're going to write our own HDL, and then we're going to go through IP integrator. And frankly speaking, we're just going to write a top level HDL code, instantiate both of them, and go through it. And the next steps would be actually to go through synthesis and basic placing and routing and generating the bit file. And you're going to end up with a .bit file that you can load to the FPGA. So once loaded to the FPGA, you're going to see that the system is not doing anything because you didn't program it. It has a processor, but the processor hasn't been programmed to do anything. So what you need to do is you need to develop some sort of application. An application is actually on the software side, which is actually the right side of this diagram. So we'll move to that. So software development, and I'd like to think about it as two parts. So in software development, what you're going to see is there's actually system code and there's also application code. So you're going to have to distinguish between these two types of codes. And what I mean by software is actually we're going to write C and C++ code, not HDL code. Your HDL has resulted in some sort of a device program, and an FPGA program with certain device, with certain IPs, with certain functionality. What we're going to be using now is we're going to be developing software in C and C++ to control that particular hardware. So this particular track tells me, okay, first, before you actually jump into writing C and C++ code, you need to figure out that you have either system or application code. And what I mean by system or application code, let me just give you an example. So all of you have written the canonical hello world example where you actually said, hey, print F or C out F and whatnot. And you just basically, whatever message you happen to put to that function actually was just displayed on the monitor. So it got displayed on the monitor, but as an end user or as an application developer, you really did not know what happened under the hood, like what happened, like what hardware happens and whatnot. And there was an operating systems and certain VGA drivers or HDMI drivers that actually took care of all of this. So what happens is there was some sort of a middle layer, an operating system in addition to some sort of a system code that took your message and interpreted and told the hardware what to do in order to do this. So this is what we're going to call system level code. And specifically, we're going to call it drivers. So a driver just basically sits between the application and the hardware and tells the hardware what the application developer wants and abstracts these ideas from the application developer. So whenever you develop your IP, not only will you write HDL code, you're going to also write some C and C++ code to actually write a driver for it. And you're going to see that the next step is actually what happens is you're going to take that driver that you just developed, you're going to take some vendor drivers and put them in here. And there's something that the IP integrator actually generates, which is hardware specification file. And the hardware specification files contain some information of vendor IPs. For example, if you're using a processor, it will tell you, well, that processor is configured to have such and such cache, such and such RAM. This is how you get the address. Like basically, there's some sort of information about how you set it up. Remember, you go through wizards to set up these IPs. So you need some information of really what did you set up? Like, did you use 200 kilobyte of RAM or did you use 200 megabytes of RAM and so forth? So what happens is you're going to take that particular file, your driver, and some vendor IPs. Like if you're using an IP that has a driver, you're going to combine them all into something we call a BSP builder. And a BSP stands for Board Support Package. And the word board is actually historic because SoCs used to be not on a single silicon chip. It used to be on a printed circuit board, and it just basically stuck. So the name stuck. So the BSP builder, what you're going to see is it ends up with a BSP library. So you're going to have a library. And this library, as an application developer, so this is your application development here or software development. Now you write the driver as a system level code, but now as an application developer, you're going to write an application level and that goes in here. And in your application, what you're going to do is you're going to include these libraries, kind of like what you did with the include stdio or iostream, depending on which language you've used. You're going to see that you include it in here, and technically speaking, you don't know what this library is doing, and you don't need to because it's abstracted from you. That's the beauty of drivers. That's the beauty of abstraction in general in programming and in computing. So you write your own application, and then you go through compiling and linking like you've done before on a desktop computer, and you're going to end up with what you used to call as a binary file. In here, we're going to call it an image file, okay? And that image file has an extension of .elf. The next step after you generated your hardware and you programmed your FPGA, and the FPGA has a processor that is blank, that is not doing anything, you went in here, you develop your driver, you went in here, you develop your application, you ended up with an ELF file. What you need to do is you need to go to the FPGA that is programmed with a hardware that is blank, and you're going to go and program some sort of software on top of that blank hardware. So technically speaking, you are reprogramming the FPGA. But frankly speaking, what you're doing is you're just programming that particular processor to do certain things with the hardware you actually did. And of course, at that point, you're going to have an FPGA chip with a memory that is completely programmed. It has hardware, it has software, so you can go ahead and test it. So you're going to see that there's actually a way, and like, let's assume you tested it and you figured out like, hey, everything is working, and you really need a single bit file. You don't want to program the FPGA, go to your Vivado, program the FPGA, and then go to your IDE and program the software. You just want to do it in one shot. What you can actually do is after you took this ELF file, you can actually go in here and go to the synthesis and routing and placing and routing and bit generation. Tell it like, hey, I do already have the software, so you can actually incorporate it in here, regenerate the bit file, and now your bit file that you actually programmed the device with already have the software because you incorporated it in it. But in order for you to do this, you have to do this first, then you have to do the L file, and then you combine it, and then you do the bit file again. Okay, so you're gonna have to do this because you're gonna have to test it before you actually incorporate it in the bit file already.